right, I'm going to skip number 1 for a second. I'm actually going to jump to number 3. Okay. The dimension of a vector space V is the number of vectors in a what of V? Basis. Good. All right, so now that we know what the definition of a dimension of a vector space is, like, let's think about number 1. How many vectors are in a basis for P3? 4. Yeah, because your basis for P3 would be 1, t squared, and t cubed. 4 vectors in that basis. Sorry, it's 4. Okay, true or false? The dimension of the null space of A is the number of free variables in the equation A equals 0. That is true. Good. About half of you used that as your question, so hopefully you got that. Notes. Okay, so some notes from 4 or 5. So if a vector space V has a basis containing n vectors, then any set in V that has more than n vectors has to be linearly dependent. Okay. Okay. Right. Yep. If a vector space V has a basis with n vectors in it, then every basis of V is going to have n vectors in it. All right, here's the definition of dimension. This was on your quiz. If V is spanned by a finite set, V is said to be finite dimensional, and the dimension of V, written dim V, is the number of vectors in the basis. So dimension is the number of vectors in the basis. We say the dimension of the 0 vector because the 0 vector is its own little vector space. We call its dimension 0. And if V is not spanned by a finite set, then it's said to be infinite dimensional, right? It has infinite dimension, and there's an example of that in your activities. So then we have another theorem. If H is a subspace of a finite dimensional vector space V, any linearly independent set in H could be expanded to be a basis for H. So any linearly independent set in H is either a basis or too small, right? You might have to add to it to make a basis. And H is finite dimensional, and its dimension will be less than the dimension of V, because it's a subspace of V. Well, less than or equal to. And then the basis theorem, this is a big one, so that's why I bolded it. If V has a dimension of P, and P is bigger than or equal to 1, any linearly independent set of exactly P elements in V is automatically a basis. Okay, so you won't have to check the 2 things that are a basis, right? So the 2 things that make a set a basis is it has to be linearly independent and it has to span the set. So now, if you have P if you know its dimension and you have P vectors, all you have to check is that they're linearly independent. They will automatically span. And same thing, if you have P and you know they span, they're automatically linearly independent, and thus a basis. All right, and then we have a little shortcut, which we'll in the demo, we'll explore why this shortcut works. But to find the dimension of the null space of a matrix, it's just the number of free variables in the equation AX equals 0. And the dimension of the column space of a matrix A is the number of pivot columns in A. And for both of those, we'll look at an example more in depth and see why those work. Okay, so today we're going to talk about dimension of a vector space. So I've created some vector spaces here, and I want to find a basis and then state the dimension of the vector space. So once I have a basis, the dimension is just the number of things in the basis, the number of elements in the basis. So first I got to find a basis. So this is the set of all vectors that look like 2a plus c, b plus d, a minus c, and b plus 3c, where a, b, c, and d are just any real numbers. So I'm going to break this out into a more parametric vector form. So a, b, c, and d are going to be like my weights, my parameters. So I'm going to have a vector times a plus a vector times b plus a vector times C plus a vector times D. Okay, so this is just a different way of writing my vector space V, just factoring out the parameters. Okay, so what has to go in my vector A to get 2, 0, 1, 0? And then for B, my first entry has no B's in it, so I've got a 0. Second entry has 1, 0, 1. Right? And then for C's, my first entry has 1 C in it. Second entry has 0. My third entry has -1, and my fourth has 3 C's. And then for D's, I've got 0, 1, 0, 0. All right, so these vectors, this guy, this guy, this guy, and this guy, right? They form a spanning set. They definitely span the set because I've written them as a linear combination that creates V. So they're definitely a spanning set. What else do they have to be if I want them to be a basis? Linearly independent. How can I tell? Column. Yeah. Yeah, so I could put them, you could just look at them. It might be possible to determine just by looking, or you can put them in a matrix, row reduce, and see if you have a pivot in every column. Of course, yeah. Yeah, you can put the vectors in any order in your matrix, yeah. So let's see, if I make them into a matrix, and I row reduce, I'm looking for a pivot in every column because that would be linearly independent. Matrix, edit, I've got a 4 by 4. Two, 0, 1, 0. All right, so when I row reduce it, I get the identity matrix, which means I do have a pivot in every column. Pivot in every column. So I have 1, 0, 0, 0. Okay, so I have a spanning set. So my starred vectors, they span V, and they're linearly independent, so they form a basis. Okay, those starred vectors form a basis, and how many of them are there? 4. So the dimension of V is 4. 4 vectors in the basis. Yeah, the number of elements in the basis is the dimension. All right, let's look at W. So this is the set of all vectors A, B, C, D, such that A plus B minus D equals 0. So I just have one equation here, right? It's not even a system. I have one equation with 3 unknowns. If I was going to try to make it a matrix to row reduce, it would look like 1, 0, oops, no, 1, 1, 0, -1, augment with 0, right? And then I'm basically done row reducing, right? I can't knock anything out. So which variable is my basic variable? Which column is my pivot column? Yeah, A is my basic variable, which means B, C, and D are all free, right? So this is pivot, and then these three are all free. Okay. So basically, I'm going to take my equation, A plus B minus D equals 0, solve for the basic variable in terms of the free variables. So I have A is negative B plus D. All right, so I'm going to rewrite W as the set of all vectors that look like, instead of A, B, C, D, such that, right? A is actually negative B plus D, so I'm going to put that in the A spot, negative B plus D. And then B, C, and D are all free, so I just put them in as they are. And that's such that, no, C is free. C is not necessarily 0. No, because B is a free variable. You always solve for the basic variable in terms of the free variables. Yep. Okay, so this is such that B, C, and D are any element of R. Do set builder. All right, now I can do this. Excuse me. I can do this problem exactly like I did the last one. Break it out into parametric vector form and try to come up with a basis. So there's no A anymore. My free variables are B, C, and D. So let's see, I've got -1, 1, 0, 0. For C's, I have 0, 0, 1, 0. And for D's, I have 1, 0, 0, 1. All right, so this is going to be my contender. I think that those three vectors might be a basis because they definitely span my set W, because all the linear combinations of those three vectors make W, generates W. So I just need to know if they're linearly independent. Thoughts? There's going to be a pivot in every column. Yep. They're linearly independent. If you weren't sure, you can, I think with this one, you can look at it and tell, because of the, if you look at the second entry, this one's got a 1, the other two have zeros. Third entry, this has a 1, the other two have zeros. This one has a 1, the other two have zeros. That doesn't tell you anything about linear independence. No, doesn't tell you about linear independence. Okay, so if you weren't sure, in this one you can tell by looking. If you weren't sure, you can put them in a matrix, row reduce, make sure you have a pivot in every column, right? But so my set, -1, 1, 0, 0. So I'm just writing this out because I want to make sure we have the right notation. 1, 0, 0, 1. Okay. This set is a spanning set because I wrote it as a linear combination. My whole vector space can be written as linear combinations of those guys. Okay, so it's a spanning set, it's linearly independent, therefore it is a basis for W, for the vector space W. And how many elements are in there? 3, which means that the dimension of W is 3. Okay, so these are the two things we were asked to do. Find a basis, give the dimension. Nope, because it was the pivot position when I put it in a matrix. Yeah. The definition of a Oh. If you wrote it like that. Yeah, I guess it's because it came first in the alphabet. Yeah. Okay, so here I've got a matrix A, and I want to find a basis for the null space. Okay, so you guys, most of you know what this is because it was your question, right? The basis for a null space, well, the dimension of the null space is the number of free variables, right? So the basis, if you remember, we learned how to find the basis of the null space last class, which was set AX equals 0, solve the equation AX equals 0, write the solution in parametric vector form, and the vectors in parametric vector form will form a basis for the null space. So I need to just augment this with zeros. And let's see, I think I have this already done. And you get 1, 0, 0, 0, 4, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. I don't have enough room to finish this. I'm going to do it on another page. Okay, so yeah, we can answer the dimension right away. How? There's only one free variable, right? So I can, this is pivot, free, pivot, pivot, right? One free variable, so the dimension of the null space is 1. So I can do that right away, because that's a shortcut. But let's make sure that the shortcut works by actually finding a basis and seeing that it has one vector in it. Okay. So if I want to find a basis, I have to take what I have here, write it in parametric vector form. So I'm going to translate this to some equations. This says that x1 plus 4x2 equals 0. This says x3 equals 0 and x4 equals 0. Okay. So this first one, I want to rewrite it so that it's a basic variable in terms of the free. So the free variable is x2. So this is going to be x1 is negative 4x2. So in parametric vector form, my solution is going to be x1, x2, x3, x4. It's my solution, right? But x1 is actually negative 4x2. And x2 is free, right? And then x3 and x4 are both 0. And then I just factor out my free variable, x2. So I've got negative 4, 1, 0, 0. So my basis is just that vector. So basis for null of A is just the set negative 4, 1, 0, 0. Which means the dimension for the null space of A is 1, because there's one vector in the basis. Hmm?
Because the null of A is 3 variables.
The dimension of the null of A?
Yes. So that's why you chose x2.
Oh, yes.
So you express everything as x2.
You express everything in terms of the free variables. Yes.
So like x3 didn't.
Right, because x3 was 0, so I didn't, x3 is not a free variable, so it didn't have to get pulled out in the parametric vector form.
So if we had two free variables, it'd be
Then there would be two vectors in your basis because you would be plus another vector with your free variable on it. Okay, so the shortcut for finding the dimension of the null space of a matrix, number of free variables. All right, to find a basis for the column space of A. So remember, again, we learned this last class. It's the pivot columns of A. So you have to do the row reducing to identify the pivot columns, right? Pivot, free, pivot, pivot. But then the basis for the column space are the corresponding columns from the original matrix. Those columns corresponding to the pivots. So we're going to have 0, 5, 1, 0. The first two rows. Right, no, you don't need them. You only take the pivot columns. Yeah. Yeah. So -2, 1, 0, 4. Skip the free one, and then -5, 14, 2, 10. So if that's my basis for the column space of A, what's the dimension of the column space of A? 3. Yeah. Yeah. Yes. Yep. Good guess. Yep. We're going to talk about that next class when we talk about rank. Yeah, so Alex look at the dimension of the null of A is 1. The dimension of the col of A is 3. Adding them together gives you 4, which was the number of columns. Yeah, yeah. Which kind of makes sense, right? Because if the dimension of the null of A is the number of free variables, and the dimension of col of A is the number of pivot columns, when you put them together, every column is either free or a pivot, so it equals the total number of columns. So so once you find the dimension for the null of A, you can automatically get the dimension for the col of A. All right, so I would like to find the dimension of the subspace of H, the subspace H of P2 that is spanned by these 4 quote vectors, right? They're not actually vectors, they're polynomials, but because it's a vector space, sometimes we generically call them vectors. All right, so the dimension of that space. So we're going to use that handy little thing that we learned last class where you can change everything to R3, right? Because this is P2, right? P2 is going to be isomorphic to R3 because P2 is spanned by 1t and t squared. Okay, so it's going to be, so my basis, my spanning set here is going to be 3, 1, 0. They're just the coefficients on the basis for P2. And then I've got 0, 2, 1, 6, 2, 0, and 0, 10, 5. Okay, so this is a spanning set. These vectors span H. Okay, these vectors span H. If I take the span of them, that builds all of H. But there's a little bit of redundancy here. How so? Yeah, so this is not a linearly independent set, which means it's not a basis, right? So if I want a basis, I need to get rid, I need to make it, bring it smaller until I have a linearly independent set. So I definitely can get rid of that one because it's a multiple of 3, 1, 0. Anything else I can get rid of? 0, 10, 5, that's a multiple of 0, 2, 1. If you multiply that one by 5, so that one can go away. Okay. Now the remaining two, are they linearly independent? Yeah. So my span, so my basis for H is just going to be those two vectors, 3, 1, 0 and 0, 2, 1, which means what's the dimension of H? 2. Oh, okay. Yeah. So that's a good question because I'm not talking about all of P2, right? I'm talking about this subset H. So H is some smaller bit of P2 that's spanned by some given vectors. Yeah. P2 is not spanned by H. H is a subset of P2. H is smaller than P2. So it's okay that its basis only has 2 vectors because it's not all of P2. Exactly. The dimension could not be more than 3. Yep. Yep. All right, so that finishes up the demo. You guys can work on the activities now.